Okay, so in the previous video, we talked a little bit about, what truth is, uh, how we're going to approach it, and what truth is specifically within mathematics. So now we're going to transition to what truth is in physics and, you know, maybe other domains. So, truth in physics is fundamentally discrete, it's granular, because when you zoom into the level of, the smallest level you can go to, first of all, you have like something called the resolving power of a microscope. You can only see that much because light itself is composed of a photon, and even if you think of it as a wave or a particle, it still has a discrete quantity, okay? And that discrete quantity interacts with other elementary particles like electrons and, you know, atoms essentially. And we can't see anything smaller than the wavelength of light. That determines what we can see or what we cannot see. And yes, we can infer the existence of smaller particles through various sophisticated means. Okay, the Large Hadron Collider, whatever. My point is, the 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 reality of the universe is, as far as we know, discrete and granular. I mean, yeah, I don't know much about space-time, the physics of space-time. Is it truly continuous, or is there some sort of particulate thing? But let's assume that, for the sake of the real world, even if it doesn't translate to the level of the atoms, I was trying to bring the level of atoms to, you know, why our measurements are fundamentally inaccurate. So there are words called accuracy and precision. Okay, so, and they're not the same. You can have, you can be precise but totally inaccurate. You can be accurate and not precise. So what is the meaning of these two words, and how does it inform, the idea of measurement in physics? So in physics, and it's also something that, informs a lot of science in general, and critical thinking, and, these sort of people who consider themselves rational, is the idea that if you can measure it, it's, it may be true, it's probably true. If you can measure it in using completely different instruments, or, different perspectives of thing, and it's the same, it gives you the same quantity, it's probably true. And there are various criteria for this that I haven't gone into, that I probably may or may not in the future. So it's probably true. So we have here this word called probably, and we know immediately that whatever absolute truth existed in mathematics is immediately lost. Okay, but now let me just come back to precision and accuracy. So suppose I am taking this scale, okay, and I want to measure a single object. And for the, let's just be really simple about it. Okay, so now we're talking about reality actually, and you can't have too many people disagreeing about reality, because it's real, it's ubiquitous, and everyone can experience it the same way. I mean, and assuming if it's like a little physical, it's a some sort of a quantity that is not within our human scale, then we'll need to rely on instruments, and these instruments need to be, uh, made the same way or having the same scale. The things that are idiosyncratic to the instrument, and then there are things that, basically, I'm talking about error. I think I'm talking about error, and what are the causes of error. So there can be causes that are intrinsic to the, there can be systemic biases. So maybe this scale is compressed slightly, and every time I make a measurement, I will be like 0.5% wrong always. And it may be helpful for me to use the scale if it's just 5% always. It's good enough for me, kind of thing. Okay, but now coming to the and there's also something called error due to um, observer erroneous observation. So maybe like I was looking at it in the wrong direction, or I was shaking a little bit while measuring something that's unique to me, or maybe like I have something very subtle. I have keratoconus or something, something, or like my eyelash is too long and I the light went to something and I saw a different result. Whatever, something that's intrinsic to, and you can't really separate what is the observer's fault and the environment's fault. Something is wrong, and you will never get an accurate measurement. That's basically the key point which I wanted to make. Anyways, coming to the thing of precision. Now, I make a line. Okay, I draw a straight line, and I'll ask you a simple question: is this line real? Is it truly real? And you can be like, yes, because it's physical. I can I can see it. I can see it, and I'm sure everyone else who isn't blind can see it. And even if they're colorblind or anything like that, they still see there's a line here. So maybe the fact that everyone sees the same thing tells me that I'm not hallucinating, or it definitely is probably real, unless I'm hallucinating other people. Anyways, but then I can measure it. So here we come to an idea that, I mean, it's a little bit lower level than mass consensus, is that for something to be true, we probably need consciousness, right? And not only we need consciousness, we need validation from n number of other sentient beings, n number of other conscious people to verify what we're doing. It's just an interesting idea. Anyways, okay, I have measured it. Let's say I've got 2 inches. Okay, and now I take it out and I do a little bit of relaxation and I measure it again. It's 2 centimeters again. Okay, I wait for a while. Now I measure it again. It's still 2 centimeters. So it represents some sort of a static quantity that I can measure consistently. Okay, so my measurements are precise. Okay, I have got consistent results. Now I told you, right, that the scale has shortened and it's like 5% shorter. So even though I have been precise in my measurements, I'm inaccurate, meaning I'm not hitting the exact value. I'm hitting it slightly short. I'm underestimating the true value. Okay, so I'm just covering this from an angle and not attacking the problem directly because I see more utility in that approach. So that is basically what accuracy and precision is. Accuracy is hitting measuring true values, what it really represents in reality. That is accuracy. You're aiming the bow to the bullseye, the center. That is being accurate always. And if you keep on hitting it in the center, you're being accurate and precise. However, if you're hitting it at the third ring consistently, then you're being precise but not accurate. So, and then there's something like Heisenberg's uncertainty principle, right? That the best measurement you can do of two quantities, you can only measure one quantity at a time. You can't measure both of them at the same time. So in physics, there are these fundamental limitations to how low you can go to measure something. I mean, how exact you can go to measure something. And this is built into the structure of reality. That's the point which I was trying to make. Mm. And another simple example would be, okay, now I'm going to use centimeters to measure this. So I'm going to like, I'm going to probably be a little bit more exact. Okay. So, okay, see here. So I have, it comes between 5 to 6 centimeters. It comes to 5 to 6 centimeters, and I don't have a gradation telling me, uh, you know, is it like 5.3? Is it 5.4? Is it 5.34? Is it 5.343? And for that, I need to have smaller gradations. And my eyes probably can't see too well on like the smallest of gradations if there were. So, and the thing is, I'll need to go down to the level of the atom to be really exact. And that's not really helpful, right? So maybe here we can also say that physics and geography are similar in that, in the use of the model and the map, right? So the idea is, when you have a map, right, it's not useful to simulate the geosphere or person's locality on some sort of representation to for it to be useful to you. It doesn't help you because there's so much of data, so much of information that you just want a map, a guideline or something to help you. Okay, it's in that direction. If I walk for, so and so meters approximately, that's good. That's great. I save so much of time, and I'll use my other senses and instincts to, guide me to where I need to go. I don't need to program, I need to go in that specific direction in that exact distance, and then turn, and then I will see this landmark and I have to walk exactly. I don't have to coordinate to that level of detail. It's unnecessary. So here we're talking about scales. So a certain scale is acceptable for it to be useful to you. And this is also the concept of um, geomap and theory. So there's this idea that, so basically, just to wrap up the geography element, is a map, right? We want to identify a good enough scale that is smaller. It's like one, if it's 1:10, 1:100, 1:1,000, depending on, you know, what exactly you're looking at. It's you have to decide which scale is good for you depending on your context. But a 1:1 scale, that's not going to be useful for the most, for most of your purposes, unless it was. But for most people, the 1:1 scale, we don't want an exact thing. We want to know something that's approximate. And we don't care if it's, we don't care if it's 5.3456. We just want to know if it's somewhere between 5 and 6, then that's good enough for me. I can get by. So there's this approximate truth is good enough. Okay, so now we're going to segue into what a theory is. So in science, there's this idea that nothing is true per se, and this is it's going to sound like I'm from anti-science or something. I'm not. There is no model that is true, but models are merely useful. So they're like a guide to truth. So it's like a map. Any theory is like a map to reality. Okay, it like says, here we go. When we have this, I don't know, I have this theory that lays out a sort of domain of truth for a given scale. So I have Newton's theory of gravity, and I throw a ball, and if I do some equations, I kind of know where it's going to land, and it's true. Now, if I use Einstein's relativity and you know at the level of light, the fact that nothing can travel faster than the speed of light, and I take that axiom and I build upon it, and I say, hey, wait, there's a correction factor, but that correction factor is small for my purposes. So the theory exists for that scale. So even though Einstein's theory is considered as the gold standard and overrides Newton's theories of motion, the truth of the matter is that Newton's theories of motions are pretty much good enough for me. So I'm just going to continue using them. And uh, now Newton's theories of motion are technically false because they do not correspond to the reality as best as we know them. Now, Einstein's theory of gravitation does correspond to reality to the best that we know, but it's always like a reservation of judgment. So it's like until some better truth is found. So if you really think about it, science is embedded in a very, it's fundamentally uncertain. It's like this boiling pot of uncertainty that actually is shielded by a domain of uh, usefulness or utility. So, what is the specific idea that came to me? Um, yes, science is not about finding the truth so much as minimizing error. Okay, so when we use science, we can say that for a given 100 statements, we can at least eliminate some of the ones that uh, we conclude are not true based on certain criteria. Now, the ones that we are left with, we can't prove that they are true, but it does seem to work. So that's something. Okay, so that is, I think, the basic philosophy of physics and science that um, I'd like to cover for now. Okay, let's let's cover the rest in another video.